Hello and welcome back. Recall in the last video we began to introduce Newton's laws, which are going to be the crux of our studies in physics for the entire semester. So this is really getting to the meat of physics right here, Newton's laws. We just have one more law that we will introduce a few more videos down the road. So his first law, an object in equilibrium has no unbalanced forces and a constant velocity. Equilibrium actually means constant velocity. We're going to focus in on Newton's first law in a moment. Second law, an object accelerates, that means its velocity changes, directly proportional to the unbalanced force that's acting on it and inversely proportional to its mass. Newton's third law, forces come in pairs. We can just simply switch the nouns in our explanation of what is acting on what to find the Newton's third law pair. In the next two videos, we will focus in on Newton's second and third law. This video will just focus in on Newton's first law. So these laws are all based on forces, and you can see the word force or forces appears in Newton's first law. So first of all, what is a force? Well, pretty simply put, a force is a push or a pull. So we can all exert forces on objects, as can Earth's gravity, as can other objects on other objects. If there's contact between two entities, then there are forces being exerted by each entity onto the other. Forces just pushes or pulls. So an object with no unbalanced forces, what does that mean? Well, remember we spent time in kinematics distinguishing between scalars and vectors, and we pointed out that forces are indeed vector quantities. So forces have both magnitude and direction. So in order to figure out whether we are in Newton's first law conditions, in other words, there are no unbalanced forces, then we need to add all of the forces that are acting on an object together. And if we come up with 0 as the answer for the sum of all forces acting, then we are indeed in Newton's first law, where the object maintains a constant velocity. So, first of all, equilibrium simply means constant velocity or no unbalanced forces. Either definition is sufficient because they mean the same thing. There are two different types of equilibrium. There's going to be static equilibrium, and that's going to be where the velocity is exactly equal to 0. Remember that the arrow over a quantity indicates that that quantity is indeed a vector. So velocity cares about magnitude and direction. So when we talk about constant velocity, then we mean that neither the magnitude or direction can be changing. Constant velocity means constant direction, constant magnitude, or constant speed. The other type of equilibrium is dynamic, and dynamic is a constant velocity, but that constant velocity is not equal to 0. So, definition of equilibrium, definition of force. Now, how do we indicate summing all of the forces together? So, sum of all forces acting on an object. This is a lot of words to write, so what we're going to do is we are going to say that this is directly equal to sigma F. Sigma comes from the Greek alphabet and is used widely in math to mean the sum of. So this is the sum of all forces acting. That's what this means. That's why this equality is written here. Instead of writing all of these letters, sum of all forces acting on an object, for shorthand notation, I'm just going to write that as sigma F. Now, you'll also see in other resources that sometimes this is going to be written as F net. It means the same thing. That means the net force. It means what's left when you add them all together. And one other way you might see this as you look at other resources is F sub R, and R stands for resultant. Okay, so again, that's what's left when you add them all together. If we are within the first law, so if an object is in equilibrium, then the sum of the forces acting on that object has to be equal to 0. In other words, there are no unbalanced forces. I'm being pulled in one direction by one person, and another person pulls me in exactly the opposite direction with the same magnitude of force. When I add those two forces together, remember forces are vectors, I would use plus and minus because I'm along one line. And so I would give a plus sign to the force that is being exerted in one direction and a negative sign to the other. And if they're the same magnitudes, then when I add those two together, I would get 0. So no unbalanced forces acting. Right now, I do not have any unbalanced forces acting. I do have two forces acting. I'm in contact with the ground. Therefore, the ground pushes up on me. I push down on the ground pushes up on me. So the force on me is the ground pushing up on me. The earth is also pulling down on me. So I have two forces that are acting on me, but when I add those two forces together, calling up positive, calling down negative, they have the same magnitudes, and with the different signs, they will add to 0. So we have to be very careful about how we add forces. When we're along one line, it's pretty easy, but remember that we spent the time looking at how to do vector addition in a plane in 2 dimensions, and that's going to be really where we're going to be looking for the majority of this semester is in 2 dimensions. So if we look at forces acting on me, I can draw what's called a free body diagram for me, or any object I'm interested in. In this case, I'm looking at forces on me, so then the free body diagram would be for me. Free body diagram. Henceforward, this is going to be an FBD. We're going to be using them a lot. From here forward, drawing a free body diagram is going to be of utmost importance in determining what forces are acting on an object. So a free body diagram really means taking the object and turning it into a dot and then drawing all of the forces as arrows, because remember they're vectors, pointing in the direction that they are acting on the object and with a length that is indicative of the magnitude part of the vector. So we're drawing a free body diagram for me. So there are 2 forces acting on me. There's the force being exerted by the ground on me, and then there's the force being exerted by the earth on me. Now, if I wanted to add those 2 together, remember, I would assign a coordinate system, and in this case I'm just on one line, so I would say this direction's positive, this direction's negative. Adding those 2 together, I would get 0. How do I know I would get 0? Because I am in static equilibrium. In other words, I am not translating vertically at all. My velocity vertically is not changing. So I know I have a constant velocity. Specifically, I'm in static equilibrium. Therefore, there have to be no unbalanced forces acting on me, and any forces that are acting on me must sum up to 0. And hence, this is the really important use of Newton's first law, is that when we see an object that is in equilibrium, i.e. it is experiencing a constant velocity, then we know for sure, without a doubt, that when we add all the forces together acting on that object, we must get 0. So we can set the equations for the sum of the forces directly equal to zero. And that's going to be very useful for us as we move through considering different problems. So next video, we will be focusing on Newton's second law.